So I think it's appropriate that we're last on the agenda because the focus for us is going to be a little bit different than a lot of the other talks. It's mostly on the chemistry side as opposed to the electrical side. But I think it's important, and it goes back to a slide that I saw this morning from Matt O'Grady on when the hockey stick is going to hit. And so today's projections is 2020, not that far away. So I look out in the crowd, are we all ready? Because there's a lot of things to do, and there's a lot of things to improve upon. So and it's all got to fit together to make it work out. So what I'm going to talk about quickly is give a quick overview of Goshen and who we are, just to show you real quick. So Goshen is the parent company. It's Chinese, and outside of China, it's called Goshen. So that's why why it's slashed there. Talk about the battery targets and the roadmaps we have as a company and how that fits with this 3 to 4 year window that we're looking at, and then the different battery systems that are available out there that we're targeting, what their advantages are and what their disadvantages are, again, mostly from a chemistry side. So as far as an overview, Goshen as a company is only 11 years old, and so there's a little bit of a financial way too fast. History of the company here. I think that from my perspective, being relatively new to the company, it's the fastest growing battery company I've ever seen in my 20 years in the industry. And so I think that it's made a lot of progress in a short period of time. And I think it is as an indication of that. I mean, you look at today, about 10% of the employees are master's and PhD degree chemists and engineers and scientists, and we have pretty advanced rate of growth that we're targeting to double that in 3 years. So again, the company is based in China in Hefei City. We have R&D there, and we have manufacturing there, mostly about 35-40% R&D, and the rest is manufacturing. And then in 6 other cities within China, there's manufacturing. So this goes anywhere from making the raw materials, putting the raw materials together in batteries, and then making battery packs for vehicles, mostly in the bus and the car market. And as far as Goshen, the U.S. or the international part of it, it's pretty much worldwide. There's some BMS design type work being done in Shanghai, but outside of China, there's U.S., which is my group, and a group in California. Germany, there's a group, and then there's another group in Japan. So these are mostly R&D, a little bit of sales, but mostly R&D type of operations from an international perspective. This is, again, as I said a minute ago, this is what we're looking at in terms of what we do. We make our own raw materials. We buy some, but we make a lot of them. So lithium LFP, lithium iron phosphate. In terms of the anode material, lithium titanate, NCM, nickel cobalt manganese, lithiated oxide, and a lot of other next generation products, specifically in the silicone area and different advanced NCM type materials. We take those materials, make those into cells, and mostly prismatic and cylindrical hard case cells, anywhere from 12 amp hours to 38 amp hours, and it's going up to 40 amp hours as we speak. And then the interesting thing about the company, from my perspective, is it goes everywhere from materials to cell to pack. It's all in one facility. Raw materials goes in one end, you make the cell, it comes out the other end and puts it into a pack, and then the packs are shipped out the door at the other end of the process. So fully integrated process. The BMS and everything is included in what we do. And I think what I like about the slide on the right here, I keep hitting the wrong button, is everyone talks about gigafactories, right? So we're at 10 gigawatt hours today, and within 3 years we tend to be at 30 gigawatts. So pretty aggressive and fast growth is what we're looking for. These are a picture of just some of the products that are our current products. You can see today we're heavy on LFP. So the first 3 designs, 2 prismatic and a cylindrical, anywhere from 10 to 25 amp hour. And then our NCM is more recent in the last couple of years, and that's, again, we're in the 40 amp hour cell capacity. So it's about 70% LFP cells and 30% because that's the goal in China is more on focus on LFP. But we expect in 3 years that'll totally flip, and it'll be majority of it will be NCM type chemistry. So where are we headed? So here's where we are as far as where we are at the beginning of making cells in 2012 to where we are today in 2017. Again, mostly focused on LFP, going from 10 amp hours up to 16 amp hours and 27 amp hours, depending on the shape and size of the cell. And you can see the energy density has gone up from 130 to 150 watt hours per kilogram. So again, I will say that's the current and into the past, but really what we see as far as the future is the NCM products shown here. So again, that started last year with a 38 amp hours prismatic cell, and we're at 43 amp hours, and we'll be in the 50s soon, just because of the need. So where does this go from a futuristic perspective? And this is kind of an indication where it is now. So I would say a couple years ago we were 165 watt hours per kilogram, and by 2019, 2020, we'll be using the materials, the high nickel materials and the silicone anode mixture with graphite, and we'll be at the short-term holy grail target of 300 watt hours per kilogram. So it's kind of like the capacities are going up, and the energy density is going up, and then the size is going down. So pretty much what the market needs, and that's where we're headed. Along with that, because this is my area of contribution to Goshen, is the electrolyte development. So you'll hear a lot about electrolyte things in the next couple slides. So that roadmap matches as well. So you have the electrolyte for LFP and NCM. It's pretty standard material. It needs a little bit of tweaking, but it's pretty good. But then as you go higher up, you need electrolytes for high nickel NCM materials. You got the high voltage NCM materials, and then ultimately you get into the high energy NCM cathode materials and the LMO high voltage spinel type materials. So it matches up, which it should. So what do we see? And again, just to set the stage here, when I say future direction and future challenges, that's in the next 4 years, 3 to 4 years. So I can tell the very last slide I'll look at past that, but this is what the challenges that exist today, and they need to be solved quickly. So the two systems I already mentioned, the LFP system, it's very stable, safe and stable, but it has limitations on voltage. 3.4 volts is the nominal voltage for the system. So it's less voltage than the NCM type materials at the bottom of the slide. It's great power performance, and so that's what we like about it. It's because a lot of our focus right now is on buses, and you need a lot of power to get the bus going and keep it going. So the challenges here is from a cell perspective is really low temperature performance. It's a not very conductive material, the LFP itself, and it's really quite bad at low temperature. So we're working on some areas because that's an automotive demand, minus 30, minus 40 degrees, depending on the region that you're in. Obviously, the colder regions, it's more of a challenge. And so we're working on that by changing the viscosity and increasing conductivity at the low temperatures. And then the system on the bottom is basically NCM. Like I said, we're a couple years into that. This is the low nickel containing systems up to the 523 type material, 50% nickel on the cathode, on the metal side on the cathode. Good system, higher voltage, 4.2, good energy performance. And right now there's no real major improvements that need to be made with that chemistry. It's just increasing cycle life. So the systems that we're working on now that are coming up, I think that are important to us is the high nickel NCM material. So this is 60% and higher, so 622811 type of cathode materials, and they're good at 4.2 volts, good energy performance. And the challenge with these is, as most people know, nickel is a good oxidation catalyst. So inside of a battery, that's a bad thing. So you oxidize electrolytes, you oxidize other components inside there, and then what you're going to get is gassing, which is going to cause your cell swelling, loss of contact inside the cell, and then your performance is going to go down from there. So how do we change that? How do we improve that? And so a lot of that can be improved through the electrolyte. If you look at this slide, here's an example of some patented technology that Goshen has. So, wrong button again. So here's your standard electrolyte. So swelling about 6 to 8%. So you can see 60-degree storage in over 4 weeks. So the first bar is 1 week, 2 weeks, 3 weeks, 4 weeks, and you can see it kind of goes up for the standard electrolyte here. And so with some technology we've developed, we got less than 2% swelling. And this is in a pouch cell, so not in the standard prismatic production cells. So you can really see a difference. If a pouch cell swells up by 5% and you have your iPhone in your pocket and it swells by 5%, you're going to know pretty quick, and because the phone's going to die on you. So, so it's a good test vehicle for us to look at this, and with that pouch cell. So we've been able to, like I said, keep it stable over the 4 weeks and keep it less than 2%. So this is an advancement that we've been working on. It looks pretty good. On the bottom half, is the other way to increase energy density is increase the voltage. So you take this 4.2 here and you go 4.35, 4.4, and that's what we're looking at as well. But again, voltage goes up, stability of electrolyte starts to become questionable. So it's another challenge on top of that, another source of gassing that you can have when you start to increase the voltage. So you got the high nickel problem to start with, and you add another problem on top of that. So this is where we start to look at the what we call the cathode SEI. So the SEI on the anode, everyone pretty much knows about, is on graphite, and that's been around for a long time, and there's a lot of good solutions to that today. But as you try to keep the electrolyte out of the cathode pores and out of the catalytic activity of the nickel, you start to put coatings and things like that on the cathode side so that it protects it as well. So an example of that is, and so this is a different system. This is data from an LCO cathode system. What you can see is, standard electrolyte, about 80% capacity retention after 200 cycles. By putting the right additive combinations, you can get up to about 95%. So a significant improvement just by the additives that help protect the cathode and also protect the anode as well. And then, of course, we want to maintain the low swelling. So again, this is the target, is to get this up and keep this low. As far as this is 45C cycling after 200 cycles, looking at the swelling. So the next system that we're working on, again, is this LTO. So LTO anode is great. You can go tens of thousands of cycles with this. So this is perfect for really applications where we really want long cycle life. And you couple that with some either LMO, but typically we're looking at NCM type materials. But again, you add another complication. LTO is notoriously for gassing, specifically on formation and even a little bit on long cycle life. So you couple that with the swelling that you get on the cathode side from the NCM, you got your problems keep multiplying. But again, so you can get some modifications to the LTO powder itself from doping and coating and things like that. And you can also look at that from electrolyte additives to how to improve that. And an example of that is here. So on this chart, we're looking at our baseline on the top line here. So the length of this white bar is proportional to the amount of gas formed. So you can go from here, you can basically cut it in half by putting the right amount of additives. But we also look at the gas that's formed, because that's critical, because the dark bars are hydrogen. So obviously electrolyte's flammable. You're producing a flammable gas. If you're worried about safety concerns like we always are, then obviously you're compounding problems. So you want to minimize that. So you can look at this case here where we've taken the ratio of hydrogen from almost say 95% over here in this particular electrolyte case, and we've reduced it to less than 50%. So a lot of tweaking and analyzing, but the idea is really, where does the additives go in the electrolyte? What do they do? And what gases are formed, and what are they reacting at the anode, are they reacting at the cathode, and trying to understand that. And this is this is the same type of analysis that we look at. So formation gassing, which are the blue squares at the bottom, we pretty much got that under control now for the LTO system, which is a big challenge. and now we're working on gassing coming from the orange bars, which are at high temperature storage. So that's what happens after aging. So you're getting gas formation. So obviously we're here at the beginning and we're working our way down on that. So that's, here's your baseline electrolyte for gas evolution during high temperature storage, and with our additives, we're basically somewhere near zero as far as the amount of gas being evolved, the quantity. So we made a good progress there, and over in this currently, obviously, impedance growth is a bad thing from a long-term calendar life, and so how do you, how do you improve that? So we made some improvements there as well. Last current system is the NCM silicone system. And so this is, like I said, this is the short-term goal. This is going to get us and people that use this cell to the 300 watt-hour per kilogram target. And typically what it's probably going to be is an NCM 811 to get the high capacity on the cathode. And it's going to be a silicone anode with somewhere between 20 to 25% silicone, and the rest will be graphite. But another complication, silicone loves to swell up when you charge the battery and put the lithium into it. So it's a physical swelling, not a gas swelling. And so again, that's another challenge. So the goal here is to really look at, plus the fact that silicone has a known large irreversible capacity loss on the first 20 cycles. And so, so we're looking at this, by changing the silicone material. We're collaborating with a couple universities on this. And then again, how do you create an anode SCI on the silicone-based material? And so this is just a quick where we're at right now. And again, from this, you can see if you take the baseline material. So the irreversible capacity loss here cannot be fixed by electrolyte. That's a materials processing on the silicone that has to be fixed to get that flat out at the beginning. But you can see that in the long run, as far as cycle life, if you take a baseline here and you add some fluorinated additives, you can increase the capacity, long-term capacity, pretty significantly. So we know in this particular case with silicone, fluorine is good. And there's a lot of development on additives that can find the right fluorinated additive. And last slide. So this is how do we get past, once we get to 300, how do we get past that? What's next after that? And so there's two basic systems that are fairly early on, but that we're looking at. That's the high voltage spinel LMNO. That's the prototypical 5-volt material. It's probably about 4.8, but people call it 5-volt material. So if you couple that with, say, an LTO, you probably say your energy density is about the same as a standard NCM material with graphite today. If you couple that with this 5-volt material with a graphite material, you can get 25% more energy density. And if you couple that with silicone, you take another increase in energy density. So this is really, something that's going to be important in the future. But of course, with high voltage, the fact is that you get more degradation of the electrolyte. So you got to protect the cathode, as I mentioned earlier, with aluminum doping and coating or other metals. And then you also have to protect it with a cathode SCI, but you also have to look at your electrolyte. So our carbonate-based electrolyte's going to be good enough for 5-volt. Maybe if you get the right coatings on the anode and cathode, it is, and maybe if you don't, then you got to go to other solvents, fluorinated solvents, and different materials like that. And finally, last but not least, the lithium anode, metal anode systems. Those are, they have long work to do. There's a bad history with these from back in the 1990s when the first rechargeable lithium metal anode cells came out, and they caused a lot of problems. So there's a bad taste in a lot of people's mouth with these materials, but there's been a lot of good work done recently about how to stabilize that lithium metal anode, and so you'll get another huge, so that the reward at the end of the day is really high with that material, because you'll get your energy density will go up significantly if you can take that lithium metal anode and put that into place. So again, that's kind of what we see as far as where we're at now, what we see in the next couple of 5 years, what we're working on to help get to the automotive market where we want to be. And so thank you for your attention, and I'm happy to answer any questions.
Thank you, Dr. Payne. I think we have time for a couple of questions.
Thank Thank you for your talk. Where do you see the future of your company being involved in microgrids if they aren't already? Microgrids?
Yeah, we're working on that. As far as a company, that's mostly done. That research is done in China, but yeah, there's a lot of work being done on that area. A lot of areas that I didn't talk about today. That microgrid is one of them. So yeah, we're working on that.
I'm not a battery person, so it's probably a pretty dumb question, but if you compare EV, kind of theme of a workshop, and home storage, microgrid type of thing, what would you see as kind of a principal differences in the requirements? Are these essentially, and what's driving advances in battery chemistry and technology? So can we pretty much use the same stuff across both, or do you see a divergence happening between the two?
There's definitely be diversions. I mean, it depends on whether you have power applications or energy applications. So cars are energy focused, especially EVs as opposed to HEVs, which are obviously more popular in the U.S. But and then microgrid and things like that. So yeah, there'll be different chemistries for different applications. And this is why I showed many different types that we're working on, because again, it'll be pretty specific to application. That there's no one battery system that's going to work for everything. No question about that.
Jeff?
Thank you for the talk. So I have a question about the cycling life. So you showed currently it's 250 watt-hour per kilogram, and in 2-3 years reach 300. So like, what's the requirement on cycling life for these energy densities?
Well, it's going to depend on the application, but if you're talking specifically about vehicle, I mean, most car guys will tell you 10 years. So I think that this is why, that's where the attractiveness of the LTO anode comes into play. Tens of thousands of cycles, make 10 years no problem at all. But you take a voltage hit and you take an energy density hit because of that lower voltage. So I think that it goes to the recycling talk that we had, or the second use talk that we had a little while ago, is each application is going to be a little different, and so therefore a battery system is going to have to match up with that. So, but it all comes down to because again, no matter what happens with a car or your cell phone or whatever, it's always the battery's fault, right? That gets all the blame. Whether it's electronics is bad or whatever, it doesn't matter. The battery's dead, so it's that fault. So that's kind of our world. We have to live with that. So cycle life is always going to be the issue with batteries. And so you can take the 300 watt-hours per kilogram target, which is in a couple of years, everyone's shooting for that in the battery world, and that translates roughly to 300 miles per charge, right? So if you get to 400 watt-hours per kilogram, maybe that's 400 miles per charge. So it's all going to kind of go up there, but there's going to be this balanced tipping point where you're going to get to the point you may get to that great capacity, energy density, but you're going to you might sacrifice on life. So it's got to be the best of all worlds. It's all got to balance out, and each system will kind of have its pluses and minuses. But I think that the NCM materials with silicone anode, that's probably the closest to a universal solution than if any of the other chemistries out there.
Okay. Are there more questions?
I remember reading about a bus line in China that recharged at the end of each run, and it used supercapacitors, and it automatically recharged at the stop. Do you have any feeling about the future of supercaps, or is the energy density still so low that it'll never compete with the chemical approach, the lithium?
I think from a supercapacitor perspective, it'll probably be a hybrid system. It'll be that with a battery, because you can obviously get huge power improvements with that system. But again, the capacities are still pretty low. So I think if ultracapacitors have a role, it'll be in a hybrid. I don't know that they're going to be self-sufficient just because of that lower capacity that they have compared to what a battery would have. But it's possible. Like I said, there's improvements every day, so anything's possible.
Okay, let's thank Dr. Payne as well.